Hello, everyone. My name is Alexandria Alcantara. I am a physics major here at the University of North Florida, and I have been working in material science research with my mentor, Dr. Jason Haraldsen, for the past 4 years. And this particular abstract is on understanding the spin glass state through the electronic and magnetic properties of manganese-doped zinc telluride. So getting right into it, this is an evolving plot of the transition temperatures as a function of their doping levels. And because the spin glass is dependent on electron mobility, you can see that the metals have a quick rise in their transition temperatures with very small levels of doping due to the high levels of conduction in metals. And this is no good for our study because there's so many electrons in the system that we won't really be able to pinpoint what's going on. And then down here we have the insulators, which insulators are very stable in their configuration. So they require larger levels of doping to induce a decent transition temperature. And then if we look at the diluted magnetic semiconductors, you can see this is kind of a sweet spot for the transition into a spin glass. And what's most prominent here is that there is a shift in slope after about 20% doping, and we found this interesting, and that's why we wanted to take a look at diluted magnetic semiconductors for this study to see if we can dope something above 20% to see if anything in the electronic system is happening. The reason why we decided to do this is because we know what materials can transition into the spin glass, and we know what temperatures, but we don't exactly know how they're transitioning into a spin glass. So this is experimental data. This is a known diluted magnetic semiconductor, zinc manganese telluride, doped with the manganese at 43% and 55%, replacing the zinc. You can see here that the system is cooling, and it follows this paramagnetic behavior. This is very similar to what our fridge magnets do. They all face one particular direction in their spins and attach to the fridge magnet. But the difference between a paramagnet and a spin glass is that as soon as the applied field is removed, the paramagnet goes right back to normal, whereas a spin glass, if it's induced by a certain transition temperature, it would actually measure remnant magnetization, so it locks onto its spins, creating a glass-like structure. So it follows this paramagnetic behavior as expected up until a certain temperature. And after this temperature, there is a cusp that occurs, and this cusp is caused by the system having to overcome a specific amount of energy to transition into the spin glass. And this is quite indicative of a spin glass, and it's shown here in this log-log plot, where you can see a previously known spin glass plotted in black and the change in slope that it has here. And then in the red is the zinc manganese telluride, where you can see that it follows almost the same exact slope. And so this is a field-cooled and a zero field-cooled protocol. What it is the system continues to cool and the field is still on. And we can see that the cusp occurs in this trial, and linear magnetization still continues to arise. And then in the zero field cool, you can see that when the applied field is turned off, that cusp is still there, and then there's remnant magnetization that's still being measured. And this happens for both dope levels. And so now the question is, can this happen at various parameters for this material? So this is a plot of the transition temperatures as a function of applied field. And you can see here that the triangles of the field cooled and the circles of the zero field cooled trace. You can see that it does transition at different levels of applied field, and then right around 1 Tesla, it drops significantly. And this is due to the energy of the applied field now affecting the exchange interactions. And so to sum up the experimental data to prove that zinc manganese telluride is a spin glass material to study, we show that there's a cusp that occurs in both field cooled and zero field cooled. We show that the spin glass transition happens at various levels of applied field. And so we can go ahead and add this to that evolving plot where you can see our points here now as stars. So we can go ahead and say that zinc manganese telluride is a suitable candidate in analyzing the spin blast behavior through its electronic properties. So we analyze the system using quantum ATK, using density functional theory. Because there are so many electrons, it can't be calculated manually. And what DFT does, it examines how the electrons move through a material. And so we started with a zinc telluride structure, and we placed the zinc atoms at 25% and 50% replacement of manganese. We use a geometry optimization to relax the figure and to assure a ground state of anti-ferromagnetic, which is expected. We use the spin polarized generalized gradient approximation and the PBE functional for a fairly large K-point sampling to properly model the system. We show that a Hubbard on-site potential is necessary to achieve the proper manganese magnetism on the 3D orbitals. And this is for that high spin state of 5/2. We also produce band structures and the density of states to see how the electrons prefer to interact. And so this is the band structure and the density of states for the zinc telluride as the mother figure. Because the band gap is around 1 eV, this means that it is a semiconductor, which is what we want. And then if we look at the total density of states, you can see that because of the equality of spin up and spin down, that it is non-magnetic, which is also what we want. If we go ahead and look at the zinc, we can see that the S and the P orbitals are interacting for the local density of states for zinc. And then the tellurium is exhibiting a P and D interaction. And because the S and D orbitals don't interact in local density of states, this can just be labeled as a P orbital interaction for the zinc telluride. So doping it with 25% and 50% manganese, you can see that there's impurity bands that start to show near the Fermi level, and they're really flat, and this is not what is expected from manganese. And so this is why we need a Hubbard U parameter, and what Hubbard U does is it's going to raise up these bands and provide more electron mobility for the system. So this is what happens when we apply Hubbard U. So Hubbard U works by creating a well around the atoms, so more potential for the system is created. And without Hubbard U, there are two issues that arise. First, being in the magnetic moment, it's way too low. It's in a spin of 2, and it should be in a spin of 5/2. And then the band gap is also very low, and experimentally speaking, the 50% should be higher than the 25%. So if we look at the magnetic moment, you can see that it is very low. And then as we apply Hubbard U, we have values of 0, 2, 4, 6, and 8. It raises up to the accepted value of a high spin state of 5/2. This is around 5.24 magnetons. And then for the energy gap, you can see that the 50% starts off lower than the 25%, which is not correct. And as we apply Hubbard U, it raises and it tapers off, and then this switch happens. So the system is still semiconductive, and that flip that is experimentally proven to happen shows. So now we can look at the system under the proper analysis. So this huge figure is the evolution of the zinc telluride doped with 25% and 50%. And this is also for the Hubbard U values of 0, 4, and 8 to compare. As I originally said, the zinc telluride was just a P interaction. But if we come down here and we look at the high magnetization for U is 8 at the manganese, we can see that the manganese is now starting to provide more interaction in the D orbitals for the tellurium, and zinc is essentially reducing from the system. And then if we go to even higher magnetization in the total density of states, you can see now that the P and D orbitals are occurring together, and the zinc is essentially being ignored. And this can only happen through the tellurium and the manganese because of those orbitals. And so we can say that the manganese is now providing polarization interaction for the tellurium. So this is a depiction of basically what's happening in the density of states. This figure was made to show what all these lines mean exactly. So for comparison, I have here the 50% doped at U equals 8 to show what we have here. So electrons have a spin up or a spin down, and the spin downs are the darks and the lights are the spin ups. The red is the manganese, the orange is tellurium, and the purplish blue is the zinc. And as I had said, the zinc is essentially being ignored from the system. That's why it's surrounded by a mostly gray area. But now the tellurium is ignoring the zinc and it's preferring its nearest manganese neighbors through these multi-node interactions. And so you can see that there is a distinct interaction in the spin density, and there's an overall change in interaction through the lattice, suggesting this is how the spin glass state forms. So with our data, we wanted to assess the spin glass transition behavior in the experimental data. And if we look at the phase diagram, a shift in slope occurs around 20%, which tells us something is happening in the system. And so in our analysis, the system shows to weaken an interaction between zinc and tellurium and shifts to manganese and tellurium, essentially shutting out zinc. So we suspect what occurs is a shift in the electronic system, allowing these electrons to interact in the lattice. And so just to wrap all that up, density functional theory was used. We use zinc telluride. We show that it's semiconducting. Doping it with manganese keeps it semiconducting. Hubbard U was necessary for the proper analysis. And most importantly, we show a possible key hybridization near the Fermi levels, which is consistent with the experimental data. And also, this was funded by the Institute for Materials Science at Los Alamos. And so shout out to them. Thank you.